In this lesson, we're going to learn all about exponential functions. And an exponential function is a function of the form y equals b to the x, where b is referred to as the base of the exponential function, and x is called the exponent. B is restricted to be only positive numbers, so you can't have a negative base on your exponential function. And also, b is not allowed to be equal to 1. So for example, if I have y equals 2 to the x, this is an exponential function where the base is equal to 2. Or if I have f of x equals 1/3 to the x, this is an exponential function where the base is equal to 1/3. But if I have the function y equals -3 to the x, then this is not an exponential function because the base has to be greater than 0. What happens is when you have a negative base, whether or not your result is going to be positive or negative is dependent upon whether your exponent is even or odd. And so in order to keep things nice and simple, we restrict our bases to values that are only positive. But not only that, we're also restricted to where our base does not equal 1. Because the problem is if the base is equal to 1, as in this case, if you let x be 2, then 1 times 1 is just 1. If you let x equal 4, then 1 to the 4th power is the same as 1 times 1 times 1 times 1, which is still just 1. So in effect, y equals 1 to the x is the exact same thing as y equals 1, which is a constant function rather than a exponential function. Some properties of exponential functions. First, b to the 0th power is equal to 1. So what this means is any number raised to the 0th power is equal to 1. So if I have 5 to the 0th power, for instance, that's equal to 1. The only restriction here is your base cannot be 0. B to the 1st power is equal to b. This should be straightforward enough because any number, if you take it to the 1st power, it would just mean to multiply it one time, which would just be itself. B to the nth power means to multiply a value n times in a row. So if you have 2 to the 3rd power, that would mean to take 2 times 2 times 2, which would evaluate to 8. So you just multiply the base n times. But you won't necessarily always have integer values for your exponents. You could also have fractions as well. And if you have a fractional exponent, that's where roots come in. So for instance, if you have 4 to the 1/2 power, that's the same thing as the square root of 4, which in this case would reduce down to 2. And likewise, negative exponents, if you happen to have a negative exponent, well, the negative exponent is telling you that your value should be in the denominator instead of the numerator. So for instance, 5 to the -2nd power is the same thing as 1 over 5 squared. You just make the exponent positive in the denominator and then evaluate. So that would be 1 over 25. Similarly, if you have 1 over 5 to the -2nd, you can take a negative exponent from the denominator and move it up to the numerator and evaluate that way. Next, we have b to the x plus y is equal to b to the x times b to the y. So this would mean, for instance, 2 to the 3 plus 2 is the same as 2 to the third times 2 squared. So the reason that this works, let me erase this and show you how it works. Next we have b to the x plus y equals b to the x times b to the y. I'll show you why this works in reverse. So for instance, if I have 2 to the second power times 2 to the third power, what that would mean is 2 to the second would be 2 times 2, 2 to the third would be 2 multiplied 3 times. Well, in effect, these parentheses aren't really necessary, and so it's really just 5 factors of 2, which is the same thing as 2 to the fifth power, which is the 2 plus 3. You're just adding those exponents together, which is the reason why that works. Of course, you would go ahead and evaluate this, and that would be 32, but I'm really just trying to illustrate why the principle works. Next up, b to the x minus y is equal to b to the x over b to the y. Same sort of principle, it's just subtracting instead. So if I have, say for instance, 5 to the fourth power divided by 5 squared, basically what happens here, I have 4 factors of 5 in the numerator, 2 factors of 5 in the denominator. Whoops, I was thinking 2 in my head. And both of the factors in the denominator cancel a factor in the numerator, which leaves 5 squared. And 4 minus 2 would be 2, so the same thing. That's the reason why that works the way it does. All right, next up, b to the x raised to the y is equal to b raised to the x times y. So the reason this works, if I have 2 to the third power squared, for instance, then that would mean to take 2 to the third times 2 to the third, and since this would all be multiplied, now it would basically be 3 plus 3. So I'm doing 2 groups of 3, which is how we define multiplication. So 2 to the sixth, which would be 64. Next up is a property that we use for solving equations, which I'll show you later in the video. B to the x is equal to b to the y if and only if x equals y. This is used to solve equations, and I'll show you how that works in a little bit. Now let's look at evaluating exponential functions. So for instance, let's say we want to evaluate y equals 2 to the x at x equals 3. In order to evaluate an exponential function, you just substitute the exponent in for the variable given. So when x is equal to 3, I'm looking at y equals 2 to the third power. So 2 times 2 times 2 equals 8. Right, when x is equal to negative 5, then I would be evaluating 2 to the negative fifth power, which, as I mentioned in the last slide, is evaluated by doing 1 over 2 to the positive fifth power, or 1/32. Lastly, x equals 1/3, so this would be y equals 2 to the 1/3 power. And when you raise something to the 1/3 power, what you're asking it to do is find the cube root of that particular number. Now let's evaluate f of x equals 1/3 to the x at x equals 3. So f of 3, just using function notation here, would be 1/3 to the third power, which is the same as taking the numerator and denominator both separately to the third power. So 1 to the third is just 1, and 3 to the third is 27. So this evaluates to 1/27. All right, when x is equal to -2, I'm looking at f of -2, which is 1/3 to the -2nd power. Now, when you raise a fraction to a negative exponent, what you can do is just flip the fraction. So, for instance, I could change this into the inverse of 1/3, which is 3, to the +2nd power. So, essentially, when you're doing negative exponents, you're doing inverses. And so that's what's really going on. This evaluates to 9. And lastly, if we have x to the 1/2, then I'm taking f of 1/2. This would be my base of 1/3 raised to the 1/2 power. And when you raise a fraction to an exponent, you can raise the numerator and denominator separately. Oops, that's the 3. Sorry about that. So 3 to the 1/2. 1 to the 1/2 is the same thing as the square root of 1. And the square root of 1 is just 1. So we just get 1 in the numerator. 3 to the 1/2 is the square root of 3. Now, what you'll soon learn is that it's not appropriate to leave square roots in the denominators of a fraction. So we need to multiply top and bottom here by the square root of 3, so that 1 times the square root of 3 is just the square root of 3. Then the square root of 3 times the square root of 3 is the square root of 9, or just 3. So now we have a square root only in the numerator, and that makes everybody happy. Okay, next let's learn how to solve some exponential equations. So the property that I mentioned earlier, a to the bth power equals a to the c, if and only if b is equal to c. That's what we're going to work off of. So basically what that means is if we can get the two exponential functions that are equal to one another and the bases are the same, we can ignore the bases and solve only the exponents. So let's give it a try. So our first example asks us to solve 5 to the 3 minus 2x power equals 5 to the negative x power. Now, the bases here are already the same, so I don't need to do any work in getting those to look the same. What I need to do is just simply start off by saying, okay, since the bases are the same, the only time that's going to happen is when the exponents are also the same. So I can immediately just start this problem off by changing it into 3 minus 2x equals negative x. Just solve only the exponents. So if I add 2x to both sides, the 2x's cancel. That leaves me with 3 equals x. And there I have my solution. And it's not necessary to check every time, but as you're learning these processes, it's a good idea to check just to see what it means when you come up with your answer. So for instance, what I'm saying is 5 to the 3 minus 2 times 3 is equal to 5 to the negative third power. So I'm just substituting negative 3 in for x, or substituting 3 in for x. So this would be 5 to the 3 minus 6. And when you do 3 minus 6, that is in fact negative 3. So this checks out. All right, let's try another one. 3 to the 1 minus 2x equals 243. Well, the issue here is that 1 minus 2x is an exponent, and it's attached to a base of 3. But the 243 is not base 3. However, if you can start your problem out by rewriting a part of your equation so that you get a base of 3, then you're set. So for instance, you may not know this right off the top of your head, but it turns out that 243 is 3 to the 5th power. And in your problems, especially on tests, you'll be given smaller numbers to work with. So if you don't know 243 is 3 to the 5th, don't worry about that. Now, The bases are the same, which means I can continue solving just the exponents from here forward. So let me subtract 1 from both sides. So 1 minus 1 cancels, so I have negative 2x equals 4. And I'll bring it up here to finish this off. So negative 2x equals 4. If I divide both sides by negative 2, those cancel, and I get x equals negative 2 as a solution. And of course, you can go back and check that and show that it works, but certainly it does. Okay, one last one here. Whoops, went too far. There we are. 2 to the 3 minus 2x equals 4 to the 1 minus x. Now, the bases are not the same, but I know that I could rewrite 4 as 2 squared and get a base of 2. The only problem here is I now have 2 to the second raised to the 1 minus x. Well, that's not so much of an issue because of all those properties I listed of exponential functions. This is where one of those comes into play. So I have something raised to an exponent raised to another exponent. I can simplify that by multiplication. So I'm just going to multiply 2 times the quantity 1 minus x, which means the bases are now the same, so I can continue solving only the exponents, just like that. And I will distribute the 2, so 2 minus 2x, and I think I'll come off to the side here, and 3x minus 2 equals 2 minus 2x. I'm going to add 2x to both sides, so that will cancel. 3x plus 2x is 5x, minus 2 equals 2. Now I'm going to add 2 to both sides to get x by itself. So 5x equals 4, or x equals 4/5. And that solves that particular problem. And of course you can go back and check, but it's not necessary every time. Let's talk about graphing exponential functions. And the basic graph that we're looking at is of the function y equals b to the x, where we're not going to be entirely concerned with the effect of the shape of the graph on the number b, that base. So your base can, at this point, just be treated as arbitrary. It does have an effect on the shape, but it's hard to do in our sketches, so we're not going to concern ourselves with it. The basic graph looks like this, where it has a horizontal asymptote at y equals 0, and that horizontal asymptote, it approaches as you go to negative infinity, but it never touches or crosses that asymptote. As you go to positive infinity, this function grows very rapidly. And one thing that sets it apart from other functions we've looked at is that it does not pass through the origin. All of our other functions so far pass through the origin, but this one does not. However, it does pass through a particular point at 0, 1, and we'll look at why in just a second. But let's state a few properties of this graph. First off, the domain of the graph is negative infinity to positive infinity. So basically, if no matter what value along the x-axis you want to plug into the function, you'll get a number back out. So you can put any number in for your exponent. The range is restricted from 0 to infinity. Sometimes it can be restricted from negative infinity up to 0, but we'll look at that when the time comes. And that just is because the graph lies entirely above that horizontal asymptote. It is 1 to 1. It will pass both a horizontal and vertical line test. And it passes through the point 0, 1. The reason is, if you plug in x equals 0 into your function, no matter what your base is, anything to the 0th power is equal to 1. So that property is coming through here, and we see that in our graphs. It's an increasing function if your base is greater than 1, and it's a decreasing function if your base is somewhere between 0 and 1. I already mentioned there's a horizontal asymptote. A couple other quick notes about this, however. Shifts and translations all work the same as before, but you need to start with the horizontal asymptote and use the point 0, 1 since the graph does not pass through the origin. So the same basic shifts and translations, the properties that we learned, work here. We just have to be a little bit more careful. Also, scaling, which means stretching or shrinking, is actually a lot more difficult because it's dependent upon the base of the exponential function. And as I mentioned, we're basically just going to disregard that for this class. So lastly, if you have a negative on the exponent in the equation, that's going to result in a horizontal flip, and a negative on the base results in a vertical flip. So it's going to flip your graph vertically. So let's look at a few examples. Okay, let's graph the following. A, y equals 2 to the x minus 2 minus 1. All right, now, the x minus 2 is in the exponent. That's going to make this a horizontal shift. So that's a horizontal shift. Remember, horizontal shifts go in the opposite direction of the sign that appears there. So this is a negative value, which means I'm going to go in the positive direction. So I'm going to go to the right 2 units. The negative 1 out here is a vertical shift, and it's going to shift everything down 1 unit. And these are the only changes that are occurring here. Now, the original graph has a vertical asymptote at 0. If everything is shifting down 1 unit, I'm sorry, I said a vertical asymptote. It's a horizontal asymptote. It has a horizontal asymptote at y equals 0, but if everything is shifting down, that horizontal asymptote is as well. So just bring it down 1 unit. And I always start with the asymptote in these. Now, normally the graph would pass through a point that is 1 unit above the asymptote along the y-axis. But now it's going to be, well, normally it would be right here at 0, 1, but it got shifted down 1 unit. So that's why I've moved down to the origin at this point, just because it got shifted. But it's also going to go to the right 2 units. So I need to go to the right 2. So this is where I would have started. I went down 1, and then to the right 2. So there's that point. And let me get rid of all this garbage. All right, so there's my reference point. Now from this point, to the right of it, the function is going to grow very quickly. And to the left of it, it's just going to approach the asymptote. So that's what my graph is going to look like. So this is a good sketch of y equals 2 to the x minus 2 minus 1. Okay, let's try y equals negative 3 to the x plus 1 minus 2. Well, starting with the easy stuff, the minus 2 on the outside is a vertical shift, and it's going down 2 units. And you can just count on that horizontal asymptote also shifting down 2 units. So I'm just going to go ahead and sketch in my horizontal asymptote down 2 units. Now, the reference point that we have, 0, 1, also gets shifted down 2 units. Okay, so it kind of moves there. But then based off of this plus 1, that's a horizontal shift, which is to the left 1 unit, because since it's plus 1, we go in the opposite direction of the sign, it's going to move us to the left 1 unit. All right, so there's kind of our reference point. I'm going to get rid of all this extra stuff. So I'm right here. But there's one other thing that's happening here. There's this negative. It's not a negative base, because remember we said earlier that the bases of exponential functions cannot be negative. So it's not a negative base. Don't think that. It's a negative number on the function itself. So it's actually like if it was a negative base, it would look like this. But in effect, the way I've written it, it's negating the entire function. So it's okay, because you would evaluate the exponent first and then apply the negative afterward. So this is okay. What it's going to do, however, is it's going to flip our graph, and it's going to flip it vertically. So this is a vertical flip. So what that means is everything that normally would have been above the axis, let me do that in red. So normally my graph would have looked like this, flips, and it moves below the axis. So it's kind of like that instead. All right, so now that you have an idea of what it looks like, let me just draw it out. This point just basically gets flipped about the axis. And that's what my graph looks like. And then I'll get rid of this red because it's not actually part of the graph. I was just showing you what's happening. Okay, so that's a pretty decent sketch there, more or less. Now, y equals 2 to the negative x plus 1. Okay, so easy stuff first. This plus 1 is just going to move that horizontal asymptote up 1 unit. So that's pretty straightforward. Now, the reference point generally starts at 0, 1, but that's my asymptote. Everything got shifted up 1 unit, so that reference point is 1 unit above the asymptote there. Only other thing that's happening here is this negative exponent. So there's a negative on the exponent. So this is going to be a horizontal flip. And it's actually a little bit more common in problems to see the horizontal flips on your graphs rather than the vertical flips. The vertical flips are a little bit trickier, but the horizontal flips are pretty common. So that's the one you really want to make sure you're getting used to. And so what happens here is originally the graph would, grow very rapidly on this side of the point and then approach my asymptote that direction. So what it's going to do is the opposite. So it's going to go very rapid on this side, approach my asymptote on the other. So I'll get rid of the red lines just to get those out of the way. Oops, I got rid of some of my blue. Put those back in. And that's how that would work. Now, the reason that that's important is because let's say you run into a graph of y equals 1/2 to the x minus 3. Here's what's a little bit interesting. So you can actually rewrite this thing as 2 to the negative 1 raised to the x minus 3, which would then simplify into 2 to the negative x minus 3. The reason you might do that is back in the properties of our graphs, what we said is that if the base is between 0 and 1, you have a horizontal flip. That's the reason why you do, because whenever you have a fraction in as your base, you can always change it into a negative exponent like we just did. So in effect, this is what we want to graph right here. All right, so minus 3, I'll start off by just pushing that vertical asymptote, horizontal asymptote down 3 units. Next, I want to find the point of reference, and it's not shifted to the left or right any, so it's just going to be sitting 1 unit above the horizontal asymptote, because if you started at 0, 1 and shifted down, you'd land right at this particular point. It's just going to be 1 unit above that asymptote. And since there's a negative on my x, that means I am going to be approaching the asymptote as x gets large and approaching infinity as x gets small. Okay, one last example with graphing. Say we want to determine a function that has the following graph. So here's the graph, and I want to come up with an exponential function that has this graph. So one thing that I want to notice is, first off, this this horizontal asymptote is shifted down 3 units. So I know pretty well how to take care of that. The function itself is going to look like y equals some base. Remember, we're not really concerned with what the actual base is. I'm just going to write 2 in for no particular reason. Raised to the x plus h plus k. All right, where h and k are kind of shifts horizontally and vertically, just being, consistent with what we did in the earlier sections. So basically, this shift down 3 is the value of k, but it tells me it's negative 3, so I'm off to a really good start here. Y equals 2 to the x plus h minus 3. Now I just need to figure out what h is, and h is going to be a horizontal shift. Now, if there wasn't any horizontal shift, my graph would have passed through the point just 1 unit above the horizontal asymptote. But it didn't pass through there. It's over here, 2 units to the right. Which means I have a horizontal shift, and horizontal shifts are always going to go in the opposite direction of the sign, so that means h is going to be, say, negative 2. So when I write this in, it's going to be y equals 2 to the x minus 2 minus 3. And the graph starts from the horizontal asymptote, goes off to infinity, so there's no horizontal vertical flips or anything like that, so don't need to worry about anything of that nature. This right here is my function. Okay, in the last little bit here, before I go into some homework stuff, I want to show you how to use your calculator to do exponents, because you may or may not have seen that in a previous class, and I just want to make sure everybody's together on how to do that. So if you just want to calculate exponents, for instance, like 2 to the 8th power, for instance, you can put the 2 in, and your exponent key is this caret that is above your division sign. So anything that comes after that caret is assumed to be in an exponent. So if you want to do 2 to the 8th power, you just put 2 caret 8, and it will do 2 times 2 times 2 8 different times and give you the answer. It also knows how to do exponents that are fractional. So if I wanted to do 2 to the 1/3 power, for instance, I come up with this particular answer here, which, with a little investigation, there's the cube root function here. If you did the cube root of 2, you'd get the same answer. So it knows that 2 to the 1/3 power is the cube root of 2. And for instance, if you want to do negative exponents, it can handle that as well. So if you did like 2 raised to the negative 3rd, so you get 0.125. which is the same thing as 1/8. So it evaluates the negative exponents correctly. So exponents are done very easily in that manner. If you want to graph, you can always use exponents in your graphs. So for instance, if you want to do 2 to the x minus 3, oh, I need an extra parentheses in here. So open parentheses, x minus 3, and then minus 2. So I would be shifting. It's a minus 3, so that's going to go in the opposite direction. So it's going to go to the right 3 units, and then it's going to go down 2 units as well. So when I graph that, it won't put in the asymptote, but you'll kind of get an idea of where it's going to be. You know, you can definitely kind of visualize it as basically right along here where this bottom of the graph is. All right, so that's at 2, as you expect it to be. Okay, next up we're going to look at some graphing in your online homework system. Okay, so I want to work with you in a homework problem here because it's not entirely obvious how exactly they want you to do this. So the first thing in this particular problem is that they want you to graph this function. And what's nice is you can pull up a little bit larger version of the function or of the graph so you can see it a little bit better. Now, the function here is 2 to the x plus 3. Now, obviously it's going to be an exponential graph, and if you look at your toolbar, you've got a line defined by 2 points and this shape that looks something like an exponential curve. That's what they want you to use. So that's your exponential curve. You select it, and you might be thinking that you're going to like drag and drop on certain points to get the graph. It's actually not like that at all. You just select in the graph, and it's just going to put the default function in there no matter what you do, which is fine. They also give you this little toolbox down here that allows you to enter the different changes to the graph. So here, the only change that we have is a horizontal shift, and since it's plus 3, it's going to go in the it's going to go to the left. So I need to put in a horizontal shift of -3 to make that graph move over to the left 3 units. All right, so now if you'll notice, the graph has changed when I put that in. All right, vertical stretching and shrinking, your horizontal stretching and shrinking, you're always just going to leave those as 1, unless you have to flip it horizontally or vertically. But you don't even actually have to do a -1 for those. There's buttons down here for reflected over the x-axis or y-axis. So that's all well and good. And the base, again, is an arbitrary thing here. You can just leave the base as 2 because that's what it's given as. But just to show you, if you enter a different base, it does change the look of the function, but not predictably so that it makes sense to use as a part of this class. So leave it at 2. And now, there's one last thing. It also wants you to graph the asymptote because it says in the instructions, if you didn't read clearly enough, to graph and give the equation of the asymptote as well. So if you go and hit save, check your answer, it's going to mark it wrong, and you're going to be wondering, why is it marked wrong? And the reason is you didn't put the asymptote. All right, to do the asymptote, we just do a line that is on the axis here because it wasn't shifted up or down. And I want to make sure that's a dashed line in order for it to be an asymptote. All right, so now that looks like what they're expecting. So when you go to check answer, oh, did I not save any of that? That's weird. Yeah, hold on one second. Let me get that back. Yes, I just hit the close window button instead of hitting the save button. You all probably noticed me doing that right when I did it. So anyhow, now I have my graph exactly as they're expecting. When I hit check answer, they'll tell me that the answer is correct. The rest of this is actually fairly straightforward. When you're answering what's the equation of the horizontal asymptote, it's always going to be a constant. So just y equals 0 in this case. And then it's going to ask about domain and range and different things, and the rest of it's fairly straightforward. But that graphing is not necessarily user-friendly, I'll say. So that should get you going. Let me know if you have questions.